Okay, so as we move to more larger and larger organic compounds, we're going to end up being able to form many, many different chemical structures from the same molecular formula. So when you have the same molecular formula and different connectivity of the atoms and it has different bonds present, we call this constitutional isomerism. So let's work through an example of this. So when we get up to a molecular formula such as C4H10, right, there's going to be two different ways we can put together this molecule. Okay? So we can take all of our carbon atoms and we can put them all in a chain, all in a row. So when we do this, I'll go ahead and draw it out in line bond notation. You can practice this in Lewis structures as well. But we can start with 1, 2, 3, 4 carbons here, right? So 1, 2, 3, 4 carbons. We count up our hydrogens. We have 1, 2, 3 hydrogens at this position, 1, 2 at this position, 1, 2 at this position. So 3 plus 2 plus 2 plus 3, total of 10. So that's one way of putting together our C4H10 molecule, right? But there's another way. We can go ahead and put 3 carbons in a row. 1, 2, 3. And instead of putting this carbon sort of at the end here, adding it on over here, we can put it in the middle. And we can form a branch structure. And this branch structure will look like this. All right? So we have two different carbon skeletons here. The carbon-carbon bonds that are present, here they're all in a chain. Here they're going to be branched. It's more star-like here. Right? So these two molecules are different molecules themselves. Even though they have the same molecular formula, they have different structures and they're going to have different chemical properties. Okay? So we can move on to a molecular formula that's a little bit more complicated. So it's still going to be C4, but this time we're going to take away 2 of our hydrogens. So it's going to be H8. Right? So again, we're going to want to have 1, 2, 3 carbon-carbon bonds, but because we took away 2 hydrogens, we're going to add another carbon-carbon bond to account for this. So for C4H8, again, we can take our molecule and we can draw it out extended like this. So 1, 2, 3, 4. So now we need to add another carbon-carbon double bond to account for those hydrogens that are missing. We have 10 hydrogens over here. We only are working with 8 now. So in this case, we can make a carbon-carbon double bond at this position, right? Let's count up our carbons and our hydrogens. So we have 1, 2, 3, 4 carbons here. Count up our hydrogens, which we've omitted for clarity, but we have 1, 2, 3, 4, 5, only 1 here, so 6, and this carbon has 7 and 8, right? So this is one constitutional isomer for C4H8. We can do the same thing here, draw out an extended 4-carbon chain. Instead of putting the double bond between these 2 carbons here, let's put it in the middle. Right? So again, 1, 2, 3, 4 carbons here. We have 3 hydrogens plus 1 hydrogen plus 1 hydrogen plus 3 hydrogens for a total of 8. So this is another constitutional isomer for C4H8. We continue to do this, so we move it from the right side to the middle. Finally, we can put it on the left side. So again, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. These 2 structures here, they are the same, right? The only thing I've done is flip it on the page. It doesn't matter if a molecule goes from right to left to right. These are going to be the same structure, right? So these aren't constitutional isomers. They're exactly the same thing, right? So these are the 2 constitutional isomers that have carbon-carbon double bonds. There are other ways of putting this molecule together. We can draw instead of putting our extra carbon bond between this carbon and this one, we could put it between this carbon and this carbon. So when we do that, we're going to form a three-membered ring, and one of our extra carbons will be sort of hanging off our three-membered ring. So if we count up our hydrogens here, we have 1, 2, 3, 4 carbons. Counting our hydrogens, we have 1, 2, 3. There's one here for 4, 5, 6, 7, 8. Right? So again, C4H8. So this one is going to have different chemical and physical properties than we see with our two isomers up here. And finally, we can make yet one more constitutional isomer. We can make a ring with 4 carbons in it. Right? So each of these carbons has 2 hydrogens, so we have 2, 4, 6 hydrogens here. Right? And so you can, when you move to larger and larger structures, just be very systematic in where you move double bonds, where you draw your methyl groups, so that you can rearrange the carbons in order to come up with all the possible chemical or constitutional isomers.